6.6 Surface integrals. We have a number of different learning objectives. A lot is covered in 6.6. Very intense. Where do we begin? Start with parametric equations. Let's get going. All right, so we've done parametric equations. We've done parametric curves. We're now going to do parametric surfaces. Our objective is to be able to integrate, where the domain of integration is going to be not just a region in the plane, flat, but our domain of integration, we want it to be any surface. If you stand in the plane, you can move to your right, equally move to your left, or you can move directly above you or directly behind you. That means that you have 2 degrees of freedom. So when we want to parameterize any surface, we will use a position vector that will take 1, 2 input parameters. So let's write this down. So we'll use S for a surface, and then we can describe a surface, S, through a position vector. If you're on a surface, you're on the surface of the Earth. The Earth is a sphere, but to us, we can visualize it locally as a plane. And we can move in one direction, or we can move in another direction. And then as we change one of those parameters, it will change our X location. It will possibly change our Y location, and possibly change our Z location. So all that we've done here is we've said that we have one input parameter, a second input parameter, and that each of the coordinates depends on these input parameters. Right. Position vector with 3 component functions, each component function depending on parameters u and v. Okay. So the point is, in contrast, that what we had studied before was looking at curves. We can find our position on a curve, but to move along a curve, you only need to move forward or backwards, so you just need a single parameter. And then we can have the curve be in the plane, or maybe, let's call that C1, maybe we have another curve which is in space, like a rocket going to the moon. And then we would need to know an X position, a Y position, and a Z position. So both of these are curves. One is in the plane and one is in space. The similarity between them is that they just take a single input parameter, because if you're going to have a curve, you start here, you want to move over there, you just have to change a single parameter t. Whereas a surface, you have a surface like this. You sit here, you can move in one direction, or you can move in the other direction. U's and V's. Very good. All right, so let's do an example. Here we have a cylinder in example 658. Let's write down S for our cylinder. Position vector. It's a surface. So this is an open cylinder with no top or bottom. Think of a soda can. Cut off the top, cut off the bottom, then you have a nice cylinder. Well, if you place that can on the table so it doesn't roll, then the walls would be perpendicular to the table. So draw the top, Draw the bottom and then the walls. So that as we take slices of the cylinder, we get circles. So it shouldn't be surprising that when we look at the x coordinate, we have cosine of some parameter, and then for the y coordinate, we're given sine of that same parameter. Let's come back here and highlight parameter u, nice and yellow, parameter u, parameter u. But we know that we're trying to describe a surface, and on a surface, we can move in one direction or another direction. And what we've done here is we have written out a point on a circle. And up until this point in the class, the circle has been in a fixed plane. And then that plane would be typically the xy plane, which is z equals 0. So we want to come up with the surface. This is in 3 space. We've already indicated 2 of the 3 coordinates. For our third coordinate, what do? We're going to use our second parameter v. Let's put that in another color, orange here. All right. So let's go ahead and open up this example from the book and see what they do. And what they're going to do is they're going to fix u and allow v to run. And then the other way around, fix v and allow u to run. And let's see what we get. All right, so continuing the example, let's look here in part A. And in part A, we have our position vector with the x, looking down here, with the x given as cosine of u, where they're letting u be k. Y coordinate, sine of u, where u has been substituted out for k. And they're saying allow k to be one of these values, 0, pi over 2, or pi, or even 3 pi over 2. So we can see that that's the intention, since they have highlighted the u value in a capital letter. So something special is going on there. What is special? They're saying let it be fixed, either this value, that value, that value, or that value. For convenience, let's take the k equals 0 case, in which case cosine would be 1, cosine of k would be 1, and then sine of k would be 0. So that's 1, 0 in the xy plane, and so that would be, over here. Okay, so that I suggested looking in the xy plane, which means that for v, that value would be 0. Let's go back and look at our point. So here, when v is 0, then if you change the value of v, that would just lift the point up, assuming that v goes positive, or if you let v go negative, that would pull the point down. And it would pull it either straight up or straight down. And then as it does that, remember that k is fixed. The only thing that's moving is v. As it does that, that would trace out a line. So for the 4 values of k that they want to consider, they're coming up with 4 different vertical lines. All right, try B. In the case of B, they're letting v be fixed. They're swapping out the z coordinate given by parameter v has been fixed at k, where k can be one of these 4 values. So then as you do that, you look at the other component functions. The other component functions only depend on u, not on v. And then you recognize that those guys, when you let u vary, that's going to be a familiar unit circle. Then where do you trace that unit circle? You trace it in the plane given by z equal to k, where k can be one of these values. So if we take k equaling 1, then that would be this circle here. This circle is traced in the plane, z equals 2. This circle here is traced in the plane, z equals -1. So then in part C, having done the work of parts A and B, we can marry these two together, trace them all in, or sketch them all in one graph, and get a visualization of what the cylinder looks like. Good. And then they bring that together here. Excellent. So that's parameterizing a surface. And in terms of doing surface integrals, that will be the starting point, is to think about the surface and come up with a parameterization, i.e. a position vector, which describes the surface. Very good.